So the first part asks us to do a mechanism regarding formation of an enol. So it's a generic mechanism, formation of an enol, and then attack of a generic electrophile. So remember, chapter 22 is all about reactions of enols and enolates. So we are going to draw our lone pairs in, and we have an acid here, and we know that acids can protonate the oxygen of a carbonyl. So we'll show that proton transfer, right, and we'll label this proton transfer. So that's made the carbonyl carbon more electrophilic, and so it's set up for nucleophilic attack. So, but we don't have a nucleophile, right? In this case, we have the conjugate base of the acid that we used. So instead of a nucleophilic attack, you might also have a proton transfer at the beta carbon. So if it was to come in and take a proton here, we could send electrons up to the oxygen that way. And that forms an enol. And the enol and what we call the keto form, because of the ketone, those are in equilibrium with one another. So those are going back and forth in solution. But we know that pi bonds are nucleophilic. So once we've formed the enol, it can actually act as a nucleophile at this carbon, right? This carbon here that I'm pointing to, and attack an electrophile. And in this case, we're just sort of using a generic electrophile. So by the way, this step was a proton transfer. Okay. And then so we can come and have it attack the electrophile. And at the same time, we can use a resonance arrow here to get to the most stable resonance contributor. So this was a nucleophilic attack. And so notice now we have attached a new electrophile, right, to this alpha carbon. So we say that this is alpha to the carbonyl carbon, which is sometimes called the ipso carbon. So the last step is just to deprotonate the proton here to get back to a neutral species where we've added in a new group, electrophilic group at the alpha carbon. Okay, so we'll label this proton transfer as well. So that is enol formation under acidic conditions. We can also have enol formation under weak base conditions as well. And strong bases though, so weak base like hydroxide, which is not a very strong, was not a very weak base, however, it's weaker than some of the other options that you could use for a base. Under strong base conditions, typically we form a enolate, which is because of the formal negative charge that's spread over the oxygen and the carbon here, the alpha carbon, it's much more nucleophilic than the enolate. So I can put in some lone pairs here and draw a mechanism, right? So in the case where we're starting out with a strong base, right, we're not going to protonate first because we're not under acidic conditions. Instead, we will do a deprotonation to form the enolate. So we can actually take one of these protons and then shift the electrons up. And this is possible if the base is strong enough. And that directly goes to our enolate intermediate, which I said is even more nucleophilic than the enol. And typically, even though the oxygen, you can imagine it might attack, it actually forms a more stable product if you use the lone pair to come down and form a carbonyl and then use the alpha carbon to do the attack on the electrophile. So this would be a nucleophilic attack. Okay. So the mechanism is a little bit different under basic conditions than acidic conditions. Okay, so let's practice drawing some enols and enolate. And remember with the enol, we have the alkene and the OH group, right? So, and it's neutral. So if we draw an enol here, we could, right, make sure to draw the alkene and the alcohol part and have it be neutral, right? So here we would form this enol, right? So far we've had symmetrical ones, so it doesn't matter. And either way, you could form an enol here. This aldehyde only has one alpha carbon with hydrogens attached. So there's only one choice here. We're forming the enol. And then this ketone only has one alpha carbon with a hydrogen because there are no hydrogens on this alpha carbon. So the enol would have to form in this direction. And then this last one is a 1,3 dicarbonyl compound. And the most stable enolate is when we form it by deprotonation on the interior carbon, because that way the conjugation extends over all 5 atoms here: oxygen, carbon, 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 oxygen. If you had formed an external enolate, there would only be a 3-carbon continuous conjugation chain. So we're going to form the enolate interior, because that's the most stable enolate that can be formed. Enol, excuse me, that can be formed. So the enolate is going to be very similar to the first case. You're just, instead of having an OH, we have an O minus. So we can basically just recopy what we had up here and have an oxygen with a negative charge. And of course it would have 3 lone pairs, but we don't need to draw that in unless we're drawing a mechanism. So we can just draw same thing we had before with an O minus. Okay, so those are the enolate structures. Okay. Next page talks about how the pKa of the protons attached to the alpha carbon, right, are typically around in the range of 17 to 20, right? So if we want to have full deprotonation, then we need to have a higher pKa for the conjugate acid of the base that we use, right? So that, because we know the equilibrium always favors the weaker acid. So we would want to have this be a weaker acid or have a higher pKa than this value. So we need to use a pretty strong base, because for example, if you had used hydroxide, then water would be the conjugate acid, and water's pKa is only about 16. So it would not fully deprotonate the alpha position of a ketone, it would only partially deprotonate it. So choosing the base, depending on what you want to do, if you want full deprotonation or partial deprotonation, careful choice of the strength of the base is necessary. So what can we use that would be strong enough, right? So one common one is sodium hydride, right? And this is really Na plus, right? And H minus, but drawn together, looks like NaH. And the structure of the conjugate acid, right, is H2, because this is the base. At H minus, when it picks up a proton, it becomes H2, and we need the pKa. I think I might have to look that one up. That's probably something like high 30s or 40s. Let's see, pKa of H2. It's going to take some time. Let's see. Well, I'm not finding it quickly. All right, I will update this later with the pKa of that, but it's pretty high, right? It's something, I think it's like high 30s or low 40s, something like that. So it's much higher than the acid. So equilibrium would definitely favor the products here, and we would get complete formation of the enolate. And then the other base that's commonly used is LDA, so lithium diisopropylamide is what that stands for. And so the conjugate acid would be the amine, right? And I don't know what the exact pKa is of this amine, but amines are typically like 35 to 38. Okay, so again, these are going to be higher, and so the deprotonation will be very much favor the products here. What is the difference between these two, right? This one is pretty bulky, this one is really small, and we can actually use that for selectivity later on. We'll see that. Okay, talking about 1,3-dicarbonyl compounds. The pKa is 10, and they're specifically talking about hydrogens, right, in the center of the two carbonyls. So those are the most acidic protons. Protons on the other alpha carbon that are next to only one carbonyl, the pKa is, as we saw before, 17 to 20. Right? So these are much more acidic because after deprotonation, we get this doubly resonance stabilized intermediate, right? So we have multiple resonance contributors we can draw here. So starting from the one we've already drawn, we can push electrons up to one of the two oxygens. So we can go this way, right, to generate a resonance contributor, and that is one enolate. And then we can also push electrons all the way to the other oxygen, right? So it's more resonance stabilized when there's two carbonyls versus only one. So that's going to make those protons even more acidic, since the conjugate base is more stable with the three resonance contributors. Okay, so explain the acidity, right? So we have the additional resonance stabilization, where the partial negative charge is on one carbon and two oxygen atoms. Oxygen, can spell today. Okay, so what base would be strong enough to completely deprotonate that 1,3-dicarbonyl compound? You would need something that has a base that has a conjugate acid whose pKa value is greater than 10. And then, is sodium hydroxide strong enough to do that? And the answer is yes, sodium hydroxide is strong enough, because if you draw out the acid-base equation, so we have our 1,3-dicarbonyl compound, we're using hydroxide as the base, right? And we're analyzing the equilibrium to form the conjugate base and conjugate acid. So we could draw one of the three resonance contributors for the conjugate base of the dicarbonyl compound, and water, which is the conjugate acid of hydroxide. Right? So when we are looking for analyzing the equilibrium, we always compare the pKa of the acid and the conjugate acid, right? So the pKa of the acid, we said these protons here, right, are about 10. And then water, right, has a pKa of about 16. So that means that this is the higher pKa, so this is the weaker acid, and the equilibrium always favors the weaker acid. And so there are about 10 to the 6 more products than reactants in this case. So yes, this is, hydroxide is strong enough. Okay, and so we can say because there are approximately 10 to the 6 more products than reactants. Okay, so that's a pretty big number. So there's not much of an equilibrium here. Concentration of this is much, much higher. And it's essentially completely converted to the products. So hydroxide is strong enough to deprotonate the interior protons of a 1,3-dicarbonyl, but it's not strong enough to deprotonate a generic ketone or aldehyde's alpha position because the pKa of those protons is much higher than this. Okay, so it says that even though you can draw it this way, right, it exists in equilibrium with its enol, and whereas normally the keto form is favored over the enol in equilibrium in terms of stability, it is not the case with 1,3-dicarbonyl compounds. These compounds tend to actually exist primarily in their enol form, and that's because it's more stable through enhanced conjugation, right? Because in this case, this was an sp3 hybridized carbon, and the 2 carbonyls are not, the pi systems are not in conjugation with one another. But here we have a p orbital here, 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 and here. So there's a 5-atom continuous p orbital system, or there's conjugation, which makes it more stable. Okay, so drawing the enol. So interestingly, in this acyclic case, there's actually an additionally hydrogen bonding going on between the lone pair on this oxygen and the hydrogen of the OH group. So it's also forming intramolecular hydrogen bonding, which also helps to make it really stable. And that's the case just when you can reach, right, where it wouldn't work over here because it's too far apart. Okay, so drawing out the enol over here. Right, we just always make sure to have that conjugated system. So its true structure is existing more in the enol form. And it looks like that in all those cases. Okay, so now we're going to start talking about reactions. So we've practiced drawing out enols and enolates, and we're going to start to see how that carbon actually acts as a nucleophile and can attack electrophiles. So we're going to be drawing a mechanism, right, where we start with the ketone, form an enol intermediate, right, and then actually halogenate the alpha carbon of the enol. So overall, we've gone from replacing a hydrogen with a bromine. So it's a type of overall a substitution reaction. Okay, so for the mechanism, because we're under acidic conditions, we should form the enol through the mechanism that we used before under acidic conditions. So we need to be mindful of the conditions in determining what sort of mechanism we should draw. Right, and so eventually we'll be getting that hydrogen involved. So I'm just going to start drawing it in from the beginning. But the first step under acidic conditions is protonation. So we don't want to forget that we don't have a base strong enough to deprotonate this position if the base is water, right? So it has to be a strong base. So instead, if we're going to be using water as the base, we need to add an acid catalyst. So that acid catalyst will protonate the carbonyl oxygen, making the carbonyl carbon more electrophilic. So first step is proton transfer. Right, now we have a situation where even a weak base such as water can come in and deprotonate. Okay. Well, I'm going to pause the video because I have a phone call coming in. Oops. Okay, sorry about that. We will continue on. Okay, so we've done our deprotonation with water to form the enol intermediate. And then now we can have a reaction with bromine, which is also in solution and is an electrophile, which can be attacked by the enol. So we can do nucleophilic attack and loss of a leaving group there. We form some bromide in solution. But water is a better base than bromide, so I'm just going to go ahead and use another water molecule for my final deprotonation. Right, and that produces the product and regenerates our catalytic acid. Okay, and under acidic conditions, typically we only add one halogen. So the next question asks us about why, even though we could form an enolate by deprotonating either side, right? So we have the possibility of forming two different enolates. We might have formed through deprotonation on the left, sorry, enols, keep calling them enolates, but they're enols, versus formation of the enol through deprotonation on the alpha proton on the right, right? So there's two different enols that are possible to form with asymmetric ketones like the one that was used in the reaction. So it is this one that's actually favored, right? Because it's more stable. Why is it more stable? Right? Because the alkene is more substituted. So if you look at the alkene itself, right, it's got 4 non-hydrogen groups, so it's tetrasubstituted. And over here, there's 1 hydrogen group, so it's only tri-substituted. So we know that the more substituted the alkene, the more stable it is, right? So that's why this one is favored. Okay, we can also do halogenation under basic conditions, although typically polyhalogenation will occur instead of monohalogenation. So let's see how we form the enolate, right? Being carefully using basic conditions to do that, and then reaction of the enolate to add the bromines. Okay, so in this case, there's only one possible enolate, and that's because there's 2 hydrogens on the left, but 0 hydrogens on the right. So this alpha carbon doesn't have any hydrogens, so no way to deprotonate there, right? But we do have hydrogens on the left, right? And so there's only one possible regioisomer for the enolate. Remember that with basic conditions, right, we don't need to protonate first. We can use our strong base to deprotonate. We don't need to protonate the oxygen first, but we can use it to deprotonate the alpha position directly, forming the enolate in one step. Okay, so that's our enolate. There's still one hydrogen here, I'm just not drawing it in. And then it can react with bromine. So we can show the nucleophilic attack here, the loss of this bromide leading group. So that has helped us add in the first bromine. Right, and we kicked out some bromide in that step as well. And then basically we go through this process another time, right? So there's still one hydrogen here. And so we can do the formation of the enolate and the attack on the electrophile again. And this will happen repeatedly for as many hydrogens that are available at the alpha position to deprotonate. So by the way, each time we are forming water right through acid-base reaction. Okay, and then we can have this process happen again where it attacks another bromine. And after this, we don't have any more alpha protons that can be deprotonated. So we stop there. Okay, and we form some bromide as well in that step. Okay, awesome. So now we have some drawing in of the products of the synthesis reactions. So we have H3O plus and bromine. So that's going to be alpha halogenation, right? Placing a bromine, and it will go on the more substituted carbon because of the formation of the more substituted enolate. Right, so we'll go ahead and place the bromine here. Right. Potassium terbutoxide is a strong, bulky base, so it will do the Hofmann elimination. Right, so instead of forming the Zaitsev product, we form the Hofmann product. And then phenylmagnesium bromide is a Grignard reaction. And so that will attack the carbonyl and form a, in this case, a tertiary alcohol from that ketone. Okay. Hello, welcome to part 2 of chapter 22, activity 1. We're going to go through the review portion of that activity. Okay, so first question says, two different compounds having the molecular formula C8H15Br are formed when 1,6-dimethyl cyclohexene, so let's draw that out. So we start out with cyclohexene. This might be 1, and then we would count this way, 2, 3, 4, 5, 6. Reacts with HBr in the dark with no peroxides. And the same compounds are formed from 1,2-dimethyl cyclohexene. So it looks like we would also form those from 1,2-dimethyl cyclohexene. So what are they? And so this is just a Markovnikov addition of HBr. So we would end up with bromine at the more substituted carbon. So this would, and then hydrogen at the less substituted carbon. So maybe we have the methyl up and the bromine down. And then this methyl might be up, and it also the opposite enantiomer of this methyl, right? And then they end up being diastereomers if we get opposite stereochemistry at those. Okay. Oh, sorry, those are enantiomers, not diastereomers. Okay, so what are those compounds? And let's see. So we would expect from this, we would also get the bromine. In this case, it's symmetrical, so it doesn't matter where it goes. But one side would get bromine, one side would get hydrogen. So we could end up with these two stereoisomers as well. Okay, a compound C6H10 contains a 5-membered ring. When bromine adds to it, 2 diastereomeric dibromides are formed. Suggest reasonable structures. Okay, so we have a 5-membered ring, and we, by the way, we can do a little, so it's C6, maybe there's a methyl attached somewhere. We can do a little calculation for HDI for this formula. So C6H10 in the HDI formula would be 1/2, 2 times the number of carbon is 12, plus 2, minus the number of hydrogen. So we have 14 minus 10 is 4, right? 1/2 of that is 2. Okay, so C6H10, I think he might have this wrong somehow, because that does not match this formula. So I think that he was intending to use this compound, but this would be C6H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Must be losing my mind here. Okay. Anyway, so it contains a 5-membered ring when bromine adds, right? So I just randomly put the alkene there and we'll try it out. And we are going to know that those bromines are going to add anti, right? So imagine the bromonium up, the hydrogen, the other bromide could attack from either side going, so that would be down. So this might be down, up, right? And then I actually think we should start with something chiral so that this chiral center doesn't vary. And then we will get diastereomers. So, because it's also possible that we would get the down bromine here and the up bromine there, and then these two are are related as diastereomers because there's one chiral center that's the same, and then two that are the opposite. So that makes sense to me. Okay. Oh, I understand now. I don't know why I was losing my mind. The 2 units of unsaturation, one is for the pi bond and one is for the ring. So that's why there's 2. Okay. I'm going to turn off my phone so we stop hearing so much dinging. Okay, so the next one is the relative rates of reaction of ethane, toluene, and ethylbenzene with bromine atoms have been measured. The most reactive hydrocarbon undergoes hydrogen atom abstraction 1,000,000 times faster than the least reactive one. Arrange these hydrocarbons in the order of decreasing reactivity and explain the trends. So this would be the most reactive, right? So we could draw an arrow for decreasing reactivity, because of course we are forming out radicals here. So if we're reacting with bromine atoms and it's undergoing what's called hydrogen atom abstraction, that's a radical reaction. So we have the formation of a radical in all of these cases. So we can figure out where is the most stable radical position in these molecules. So for the aromatic compounds, it's the benzylic position because of resonance stabilization. And then for propane, there's a probability of doing radical abstraction from these 3 because there's 6 total hydrogens there and only 2 here. However, this is the most stable of the 2. So benzylic and resonance stabilized is definitely more stable. This being secondary in benzylic, primary in benzylic, and then just secondary. Okay, deduce the structure of each of the following compounds on the basis of their proton NMR spectra and molecular formulas. Okay, so unfortunately it's given to us as this sort of data and not a spectrum, which is always preferred. I'm kind of a visual person, but we will do our best here. So we have C8H10, which the HDI formula for that would be 1/2 2 times 8 is 16 plus 2 minus 10. So we have 4, and whenever I see 4 or more, I start thinking about an aromatic ring, because an aromatic ring is a ring, so that's 1 unit of HDI, and then 3 pi bonds would be a total of 4. So let's look at the data here. So we have, if I'm thinking about an aromatic ring, I kind of look over here and I see this 7.1 ppm. So that's an indication that there's probably an aromatic ring. And you might be a little bit confused about the fact that it says a broad singlet. It's a little weird, right? But what you should know about aromatic protons in an NMR is that even though they might not be equivalent, they can still overlap. And especially for a phenyl ring, it can even look like a singlet, even though there should be splitting. And the fact that you have multiple signals that are splitting overlap, it kind of looks like this broad peak. So that's where the broad singlet comes in. And I'm thinking that it only has 1 substituent because it integrates for 5 hydrogens. So that means that, right, it should have 5 hydrogens total. So I'm putting that fragment here for the 7.1 ppm broad singlet. Of course, in reality, there should be 3 different signals here, right? We have these 2 protons which are equivalent, those 2 protons which are equivalent, and then this one. So there's 3 different signals It's just that they're not differentiated, so they might overlap, and that's why the aromatic region can be a little bit tricky that way. All right, let's see what else we have up here. So it looks like we have a something that integrates for 2 hydrogens. So I'm going to draw a little, I'm going to put my information over here and then draw a little fragment. Okay, so 2 hydrogens, and I'm thinking CH2, right? And it's a quartet, so I'm thinking it's got 3 neighbors and probably none on the other side. And that makes sense, particularly if it's benzylic, then the shift is usually at around 2.5. So that definitely makes sense. And then my other signal is 1.2 ppm, triplet, 3 hydrogens. So I have 3 hydrogens, I'm going to write CH3. It's a triplet, so it has 2 neighbors. I'm going to write a CH2 next to it. Circle the ones that the actual signal for. And so then this really coming together to look like ethyl benzene. And just double check that your chemical shifts and everything match that. And it looks good to me, especially with the benzylic hydrogens coming at around 2.5. Okay. The next one we have is C10H14. And we can do a little calculation here. 1/2, 2 times 10 is 20, plus 2 minus 14. So 22 minus 14 is 8. So again, 4. So I'm kind of thinking aromatic ring. I come up here and look at, okay, there's a multiplet in this range, right, integrating for 5 hydrogens. So that's my first signal, right, and this says it's a multiplet. That's kind of a name we give to anything that doesn't have a specific splitting pattern that we can identify. Integrating for 5 hydrogens. So again, because of the shift being around 7, I'm thinking aromatic ring, 5 hydrogens, so I think it's a mono-substituted aromatic ring. Okay, so let's see what else is attached here. And we only have one more signal. It's at 1.3 ppm. It's a singlet integrating for 9 hydrogens. So whenever you see a singlet integrating for 9 hydrogens, it's characteristic of a tert-butyl group, where all 9 hydrogens of these 3 methyls are equivalent. Right, so putting that together, we come up with tert-butyl benzene, and the shifts all make sense for that. Okay, the next one is C6H14. So a quick HDI is 1/2, 2 times 6 is 12, plus 2 minus 14. Right, so 1/2 of 0 is 0. So we don't have any double bonds at all, or rings in this particular structure. All right, so let's look at what we are looking at. So for a signal, 0.8 ppm, doublet, 12 hydrogens. So 12 hydrogens is very unique, right? How do you get 12 hydrogens that are equivalent? So there must be some sort of symmetry, probably 3 different or 4 different methyl groups is my thought. So with some sort of internal plane of symmetry making all of those methyl groups equivalent. Okay, so let's see about the other signals. So we're at 1.4 ppm, septet, 2 hydrogens. Okay, so for a septet, right, then this has 6 neighbors, right? So maybe 6 neighbors, and then this one was a doublet. We didn't really think about that before, right? So if it's going to be a doublet, maybe it's attached to a CH, because it can only have one neighbor, right? So kind of coming up with some symmetry here. Maybe it's attached that way. And then septet would mean that this hydrogen has 6 neighbors. You might be thinking, doesn't it have 7 neighbors, like if you include this one? But remember that equivalent hydrogens, and these are equivalent by symmetry, equivalent hydrogens don't split one another. So it actually doesn't see this neighbor. Instead, it just sees this 6. So it makes sense that this would be these CH groups, right? And the this signal, right, is for the methyls, right? Okay. All right, so kind of drawing it a little prettier might look something like that. Okay, last one here. We have C6H12 HDI 1/2, 2 times 6 is 12, plus 2 minus 12. So equals 1. Right? So we have one pi bond or 1 ring. Okay, so something to think about. And then as we look at the different signals here, if I'm concerned about, okay, do I likely have a pi bond? I might want to look in that region of 4.5 to 6.5. Because if I have any hydrogens attached to a pi bond, they'll show up in that region. So I do actually see this signal here at 5.1 ppm. And it's a triplet that integrates for 1 hydrogen. So that 1 hydrogen, again, because of the shift, I'm really thinking that it's attached to a pi bond, a carbon that is making a carbon-carbon double bond. And let's see, if it's a triplet, right, then how many neighbors does it have? It has 2 neighbors. So perhaps attached here, here, or here, it has 2 neighbors. So we might think about maybe it's got a CH2 here, right? Or perhaps there is a CH2 here. Okay, so one of those. Either way, that would make it a triplet. So kind of keeping that in mind, let's see what else we've got. We have the next signal is 1.7 ppm. It's a singlet for 3 hydrogens. Right, so this one, if it's 3 hydrogens, I'm thinking CH3. It's a singlet, so it's not got any neighbors. One way to maybe do that is to make it attached to the alkene with maybe something like this, right, where there's nothing here, so no neighbors, no additional neighbors. We'll consider that. Okay, 1.6 ppm, singlet for 3 hydrogens. So that's another one that's not exactly equivalent, another methyl. So perhaps we have kind of pretty much the exact same signal, but 2 of them. So we'll think about how to put that together. And then the last signal, we have 0.9 ppm, triplet, 3 hydrogens. So that's a CH3 because of the 3 hydrogens. It's a triplet, so it has 2 neighbors, right? So that's an important piece of information here as well. So we're kind of putting all of those together see if we can come up with a structure. Maybe a little more space here. Okay. So if we put that all together, maybe we have an alkene. Looks like we do have an ethyl group. Let's see that anymore. Right, because we have this CH2CH3, so maybe one of them, there's an ethyl group, and then I need at least one hydrogen attached, so maybe here, maybe there, and then two methyls where there wouldn't have any neighbors. So let's see, maybe I put the two methyls here and the hydrogen there, or let's see if there's another possibility. Could I maybe put the methyl here and here and have the hydrogen be over there? Oh, you know, this is a little too far away actually to be a neighbor, right? Because this is attached to the carbon attached, so actually it cannot be this. I don't know what I was thinking before. So I think this is not a possibility because this just, this hydrogen actually doesn't have any neighbors. So this would be a singlet. So we are looking at most likely this one because of the two neighbors here, making that a triplet. All right, so I think this one is the winner, the structure here. Okay, and I think it's always a little better if you can actually see the spectrum. There's more information to play with there. Just visually, it's easier. Okay, so now the next part is using 1-bromobutane and any necessary organic or inorganic reagents suggest an efficient synthesis for each of the following alcohols. So it looks like we have to start with 1-bromobutane, and we need to get to, for example, 1-pentanol. Okay, so it looks like we need to make a new carbon-carbon bond here. So perhaps we can use a Grignard reaction, right? And the reagents could be magnesium and formaldehyde. And an acidic workup. Okay, that would work. How about 1-bromobutane to 2-hexanol? So 4, 5, 6 with an alcoholic carbon number 2. Okay, so it looks like we're making a new carbon-carbon bond. We'll use another Grignard reaction. In this case, we're making a secondary alcohol, so we're going to use an aldehyde. Okay, the next one, we're making 1-phenyl, 1-pentanol. Okay, so there's pentane, 1-pentanol, 1-phenyl. So phenyl here as well. So again, another Grignard with a different aldehyde in this case. Okay, the last one, we are making cyclobutanol. Okay, cyclobutanol and 1-butyl. 1, 2, 3, 4. So it looks like we are making this carbon-carbon bond. So in this case, we need a ketone to make a tertiary alcohol. Cyclobutanone would be the ketone that we want. Categorize the following as aromatic, anti-aromatic, or non-aromatic. So this looks like a highly polarized bond, right, where the electrons in that pi bond would actually exist much more on the nitrogen. And if that was the case, then you would get, this is a much more significant resonance contributor. And then this is the tryptolium ion. So this is aromatic. So this I differentiate from the key here on this one. So anisole has an aromatic ring. Phenyl ring is aromatic. This is aromatic. 6 electrons if we count one of the lone pairs in a p orbital, and then the other 2 electron pairs makes an odd number of electron pairs. So this is aromatic. In this case, none of these 2 lone pairs count towards aromaticity because that atom is already participating in a pi bond. So this looks like benzene to me and is aromatic. And then cyclobutadienes are anti-aromatic, particularly if you assume that the p orbitals are coplanar. Okay. So an IUPAC name for this compound. So this is going to be named as a ketone. So that's the highest priority group there. So it looks like we've got a phenyl and 2 ethyl substituents. E comes before P alphabetically. So we will do 3,7-diethyl and 9-phenyl. Okay, and then so let's see, non-N, 2-one, because it's named as a ketone. And then we do need to worry about the stereocenters as well. So in terms of priority, this carbon, and this carbon is a tie, and then there's a hydrogen pointing back here. So moving on to this carbon, and this carbon, these 2 are a tie. This is definitely going to be the last priority. So this is priority 3. And moving on to this one gets priority. So it's going to be 1, 2, 1 to 2 to 3 clockwise with the hydrogen pointing back. This one is R. And then here, this will be priority 1, 2, 3, right? 1, 2, 3, the hydrogen again pointing back. That's counterclockwise in S. So we have at the very beginning 3S 7R. So it says 1 has S configuration at both chirality centers. How is it related? So that would be the 3S 7S. And these are related as diastereomers because they have one of the stereocenters the same and the other one opposite. You can't see that very well, sorry about that. But up there. Okay. All right, so as always, post in the discussion section if you have any questions about this. Thank you guys, see you later.